Instruction pipelining, a technique that boosts CPU performance by overlapping the execution of multiple instructions. It divides the process into 5 stages. Fetch, retrieves the instruction from memory. Decode, interprets the instruction and prepares control signals. Execute, performs calculations or operations. Memory access, reads/writes data from slash to memory, if required. Write back, saves results to registers. By processing different stages of multiple instructions simultaneously, pipelining increases throughput without raising clock speed. The image clearly lists these stages, highlighting the streamlined flow of instructions in a CPU pipeline. Factory assembly line analogy to explain CPU pipelining. Pipelining explained. Compares CPU stages to factory workers, where each worker, pipeline stage, specializes in one task: fetch, decode, execute, etc. Just as multiple products are built simultaneously in an assembly line, multiple instructions are processed concurrently in a CPU pipeline. Without pipelining, describes a slower, sequential approach. One worker, CPU, must handle all stages of an instruction before starting the next. Like a single worker building an entire product alone, this method is inefficient and slow. Key takeaway: pipelining maximizes efficiency by parallelizing work across specialized stages, dramatically improving instruction throughput. The analogy makes the technical concept intuitive.
Pipeline execution example breakdown. This image demonstrates how instruction pipelining works over multiple clock cycles, showing how different instructions progress through each stage: fetch, decode, execute, memory, etc., simultaneously. Key observations: parallel processing. Unlike sequential execution, where one instruction must finish all stages before the next starts, pipelining allows multiple instructions to be in different stages at the same time. Example: Cycle 1. Instant 1 is in fetch. Cycle 2. Instant 1 moves to decode, while Instant 2 starts fetch. Cycle 3. Instant 1 reaches execute, Instant 2 is in decode, and Instant 3 begins fetch. Efficiency gain after the pipeline is filled. Initial cycles where stages are still being occupied. The CPU completes one instruction per cycle, e.g., by cycle 5, Instant 1 finishes while Instant 5 starts. Without pipelining, each instruction would take 5 cycles to complete, 1 per stage. Visual clues: the numbered instructions 1, 2, 3 show how new instructions enter the pipeline each cycle. The staggered placement of stages, e.g., Instant 2 decode below Instant 1 execute, emphasizes overlapping execution. Why this matters: pipelining hides latency. While one instruction is in memory access, another can be in execute, keeping the CPU busy. The example shows how this achieves higher throughput, more instructions completed per cycle. Real-world pipelining examples: Apple M1, deep pipeline, 8-wide decode, with smart forwarding and branch prediction for max performance. Intel i7 uses out-of-order execution to reorder instructions and avoid stalls dynamically. ARM Cortex, simple 5-stage pipeline optimized for battery life in mobile embedded devices. Each design balances speed, power, and complexity differently. Software tricks for faster pipelines: compilers optimize code to prevent pipeline slowdowns by reordering instructions to avoid data conflicts, unrolling loops to keep the pipeline busy, predicting branches to minimize stalls. . Pipelining in the real world, pipelining isn't just for CPUs, it turbocharges efficiency everywhere. Factories, cars, phones built in stages, like CPU instructions, data systems, Kafka, Flink process data in steps, ETL pipelines, software DevOps, code right pointing arrow test right pointing arrow deploy happens automatically. Graphics GPUs renders frames in parallel stages for smooth gaming. Pro tip: any multi-step process can benefit from pipelining. Understanding data hazards in pipelining. This image explains 3 types of data hazards that can occur in pipelined processors when instructions depend on each other. 1. Raw, read after write, true dependency, problem. An instruction tries to read a value before a previous instruction has written it. Example: add R1, R2, R3, writes to R1 sub R4, R1. R5, reads R1, must wait for ADD to finish, fix. The pipeline must stall or forward the result from ADD to sub. 2. WAR, write after read, anti-dependency, problem. An instruction tries to write to a register before a previous instruction has read it. Example: sub R4, R1, R5 reads R1 at R1, R2, R3 writes to R1, must wait for sub to read R1 first, fix. Requires proper register renaming or scheduling. 3. WAW, write after write, output dependency, problem. 2 instructions try to write to the same register, risking incorrect final value. Example: add R1, R2, R3 writes to R1 sub R1, R4, R5 overwrites R1, must execute after add, fix. Ensure instructions complete in order or use out of order execution. Key takeaway: raw is the most common hazard, fundamental to dependencies. WAR and WAW arise from pipelining, parallelism, and are mitigated via techniques like forwarding, stalling, or renaming. How to handle pipeline hazards. This image outlines 4 key techniques processors use to mitigate data hazards in pipelined execution. 1. Forwarding, bypassing. What it does: directly routes results from one pipeline stage, e.g., execute, to another, e.g., decode, before they are written to the register file. Example: if ADDR1, R2, R3 is in execute and sub R4, R1, R5 needs R1, the result is forwarded immediately. Pros: reduces stalls. Cons: requires extra hardware wiring. 2. Instruction reordering. What it does: the compiler, or hardware like out-of-order execution, rearranges independent instructions to separate dependent ones. Example: swapping ADDR1, R2, R3 and LDR6, R7, if no dependency exists. Pros: maximizes pipeline utilization. Cons: complex to implement, may need speculative execution. 3. Stalling, pipeline bubbles. What it does: inserts a bubble, no op, to delay subsequent instructions until data is ready. Example: a raw hazard forces a one-cycle stall to wait for ADD to complete. Pros: simple to implement. Cons: wastes clock cycles, lowering performance. 4. Hazard detection units. What it does: dedicated hardware monitors instructions in real time to detect hazards, e.g., raw, WAR, WAW, and triggers fixes, stalls, forwarding. Pros: automated and comprehensive. Cons: increases chip area and power usage. Key trade-offs: performance versus complexity. Forwarding and reordering boost speed but add hardware, logic overhead. Flexibility versus cost. Hazard detection units handle edge cases but are expensive. Performance impact of hazards. Simple explanation: this image shows how pipeline hazards slow down CPU performance. Comparing ideal versus real-world scenarios. The goal: in a perfect 5-stage pipeline, you'd get one instruction per clock cycle, max speed. Formula: throughput equals instructions divided by clock cycles. The problem: hazards, like data conflicts, force stalls or bubbles, wasting cycles. Real-world throughput is lower because the CPU sometimes waits instead of working. Solutions shown: no pipelining, slowest, one instruction every 5+ cycles. Basic pipeline, faster but suffers from hazards. With forwarding, fewer stalls, better performance. Full optimization, best case, near one instruction cycle. Takeaway: hazards are like traffic jams in the CPU, they ruin the ideal speed. Fixes, like forwarding, help, but perfection is hard. Control hazards happen when your CPU hits an if statement dilemma. The pipeline tries to fetch the next instruction, but doesn't know which one to grab yet, because a branch jump decision is still being calculated. Consequences: pipeline might load the wrong instructions, wasted work, causes stalls while waiting for the decision. Common culprits: if-else conditions, loops, function calls. Pipeline hazards cheat sheet. Traffic lights. Pipelining speeds up CPUs but creates two main headaches. Keycap 1 data hazards when instructions step on each other's toes. Raw. Need data before it's ready. Most common, WAR, WAW. Messy register writes. Keycap 2 control hazards. CPU gets confused by if statements and jumps, doesn't know which instruction comes next. Why it matters. Checkmark hazards cause stalls equals slower performance. Checkmark: modern CPUs use forwarding, branch prediction, and out-of-order execution to cope. Fun fact: a perfect pipeline would be 5x faster. Hazards are why we don't get that in reality.